All right. Good evening, everyone. Thanks, Mrs. Burnett, for that prayer. And again, she would have highlighted that this is Matrices Part 2. So Part 1 is actually on YouTube. You can always check it out on YouTube, and the link will be placed in the chat in another few moments or so. All right. So Matrices Part 1. Sorry, Part 2. So we have a little icebreaker, but before we get to the icebreaker, we have some items that we will be looking at for this PowerPoint presentation or this workshop in general. All right, some things that you might need. Well, you will need. You will need a calculator, a pencil or a pen, and a notebook. All right, so these are the things that you will be needing this particular session. So at the end of today's session, and probably more, you'll be able to evaluate the determinant of a 2x2 matrix. You will be able to differentiate between a non-singular and a singular matrix, as well as obtain what we call the inverse of a non-singular 2x2 matrix. And we'll get to why we don't have inverse of a singular matrix, which you'll see shortly. And finally, we want to use matrices to solve simple problems in arithmetic, algebra, and geometry. In other words, we're solving linear, simultaneous, or simultaneous equations with two unknowns. All right? So we have three matrices. We have matrix T, U, and V, as you're seeing on your screen. All right? And we have a good amount of questions to complete. So we have 5 questions. If you were here in the previous session, this would have been given as homework, and we'll also verify that the results that you got if you were present at that time. But if why the matrix product TV is not possible, not actual TV, but the matrix multiplication of TV. All right. So what comes to mind? We need to identify the two matrices, which are T and V, respectively. All right. So we identify them. So we write them down. Technically speaking, we write them down because we want it to be there for us to understand a bit better. All right. The next thing that we want to do is to check if those matrices are compatible. And what's another word for compatible that you might see in matrices? Conformable. All right, so you might see compatibility or conformable. All right, so how do you know when matrices, or when you're multiplying two matrices, or even adding or subtracting matrices? How do you know if they are compatible? Can anyone tell me in the chat? Could anyone tell me in the chat? How do you know if two matrices are compatible? Can anybody tell me? I'll give about 5 seconds. All right, let's see. So we have the matrix T. Now, why is there a 2x2? That's how we actually call it. Now, it has 2 rows, and rows go from left to right or right to left. So we have 2 rows and we have 2 columns. So that is how we get the 2x2. Now, what about matrix V? How many rows and columns are we seeing in matrix V? You can type in the chat as quickly as possible. How many rows do we have in matrix V and how many columns? How can we write that? Any takers? All right, 3 rows, 2 columns. All right, fair enough. I think this person is from Norma Manley, if memory serves me right. So we get what we call a 3x2 matrix. Now, when you see the 2x2, the 3x2, what is another term that we use to describe that 2x2 or 3x2? What is a term that we associate with matrices? Can you tell me? You might hear of order of a matrix, and you might also hear about the size of the matrix. All right. So generally speaking, those are the terms that we could use to describe what the 2 by 2 and the 3 by 2 represents. And always remember rows versus rows and then columns. So you start with the rows, then you go to the columns. All right. So to check compatibility, we use the inner dimensions. So as you can see on the screen right now, the arrowheads, those represents the inner dimensions of the matrices, 2 and 3. So we actually say that they're not compatible. Why? Because the number of columns in the first matrix, which is matrix T, is not equal to the number of rows in matrix V, which is the second matrix. So 2 is not equal to 3. So they're indeed not compatible. All right, is everybody on the same page? You can give me a thumbs up, thumbs down if you're not understanding. You can go ahead, tell me. Are we on the same page? Yes, no? Anyone? You can speak if you want to, or if you can. All right, let's go. So this is how we show compatibility. All right, good. So that's how we show compatibility as it pertains to matrices. All right. So the second question. So it says state the order of matrix, the matrix product of TU. Now again, we want to write down our matrix, our matrices that we're going to multiply. So T, then U. All right. So that's what we have. We have TU. Can anybody tell me what is TU again? As in, what is the matrix T? What is the order of that matrix? What is the order of matrix T? How could we write that? And you can type in the chat again. What is the order of matrix T? And you can also give me the order of matrix U as well. All right. Are both of them 2 by 2? Are both matrices 2 by 2? Yes, no, maybe, sure, good. All right. So I'm seeing 2 by 2 in the chat. So they are indeed 2 by 2. So we got the order of matrix T and U, which are 2 by 2. Both of them are 2 by 2. So the first thing that we need to check, we can't just say, oh, they can be multiplied. The first thing that we need to check is their compatibility. So are the two matrices compatible? And how do you know? Any takers, you can type in the chat. All right, yes, how do you know? Yes, how do you know? What did I mention earlier that we could use? Or what statement could I use to justify that these two are actually compatible? And you can always turn on your mic if you can't type so fast. All right. So we use the inner dimensions, which are the 2 and the 2. But in this case, in order to show, besides the compatibility, which we would have discovered already, it's at 2 rows is equal to the two number of rows in matrix T is 2, and it is also equal to the number of columns. Sorry, amount of rows, columns and rows, sorry. So the number of columns in matrix T is 2, and it's equal to the number of rows in matrix U. So they're both compatible. So how do we get the matrix product? We say it's the outer dimension. So now you see the arrowheads going at the outer dimension, which also indicates a 2 by 2. So when you multiply matrix T and U together, you will get a 2 by 2 matrix. Your result will be a 2 by 2 matrix. All right, so you'll have 2 rows and 2 columns in that matrix product or its resultant or answer. So the matrix product of TU is indeed a 2 by 2. Now, they want us to calculate the matrix product of TU. So again, the first thing that we write our matrices. So we have T, then U, or followed by U. All right? Now, how do we multiply matrices? Can anyone tell me? Does anyone remember how we generally multiply matrices? What do we normally say? How could we do this? All right, so we multiply the row by column. So that is why it's so important to remember that thing about row by column. So let's go. So the first row in matrix T is going to be multiplied by the first column in matrix U. So what does that give us? It gives us, we checked the compatibility already from the previous question, so we don't have to check it again, all right? So that gives us 2 multiplied by 1 added to 1 multiplied by -5. So that is the first row in the first matrix, which is 2, 1, multiplied by the first column in matrix U, which is 1 and -5. What about the second row, the 4 and the 3? What will that be multiplied by? So again, the 4 and the 3, what will we multiply that by? Can anyone tell me? The 4 and the 3, the second row, what will we multiply that by? Any takers? All right, same at the, all right, cool. So we multiply 4 by what? What do we multiply 4 by? 4 multiplied by? All right, 1, and then, all right, good. And then we multiply 3 by -5. Now, what do you notice? Are you seeing anything that is similar, different? What are you seeing? Do you notice anything that you can use to remember how you should be multiplying matrices? Anything in particular that you can use? So the brackets going from top to bottom, all right, will be the same numbers, or digits, I should say. All right. So what about, are we finished right there? Should we leave it as that and that's our answer? What else should we do? Should we do something else? What should we do? All right. So we multiply, we continue. We finish the first column in the second matrix. So we need to get to the next column, which has the 6 and the 4. So we're going to repeat that step that we did earlier, but instead using 6 and 4. So the first row of 2 and 1 will be multiplied by the column of 6 and 4, the second column in matrix U. So that gives us 2 multiplied by 6 added to 1 multiplied by 4. Now, what do I multiply 4 by now, which is in the second row? 4 is multiplied by what? What digit should I multiply the 4 by? Can anyone tell me? What digit should I multiply the 4 by? All right, the 4 by 4, you sure? Remember, there's a trick. The top and bottom brackets will be the same. So what should I multiply 4 by? All right, 6. All right, good. What about the 3? Yeah, no, 6. Okay, you corrected yourself. That's good. What about the 3? What do I multiply the 3 by? The 4. All right, fantastic. So again, you can use that little thing, the brackets thing, to make sure the top and bottom brackets are the same values. All right? So that indicates that you went from the first column and the second column. All right? And if you had a third column, once it's compatible, that is, then you'll have a next set of columns. So we multiply. 2 by 1 gives us 2. 1 times -5 gives us -5. 4 times 1 is 4. 3 times -5 is -15. So what would be my final result now? When I add 2 added to -5, what do I get? 2 added to -5, what do I get? What do I get when I say 2? All right, -3. All right, and I think the others will be self-explanatory. So 4 added to -15 gives you -11. 12 added to 4 gives us 16. 24 added to 12 gives us 36. Now, can anyone tell me the element that is found in the second row and the second column? What element in this matrix product of TU will that be? So the element that is in the second row and the second column. What element is that? Could anyone tell me that element? In this matrix product of TU, what element is in the second row and the second column? Can anyone tell me that one? Any takers on that? All right. So the first row is -3 and then 16. The second row is -11 and 16. The first column, the elements are -3 and negative 11. The second column elements are 6. So which one would I pinpoint to get the second row and the second column? Which element is in that second row and second column? So that would be 36. All right? So that would be 36. U, it's given, okay, yes, 36, the normal monthly student. Good. All right. So if W is equal to 2 times the matrix U, or 2U, determine W. You might ask, oh, I get you, that's fine, man. It happens. You might ask, but they never gave us W. So they gave us T, U, and V, matrices T, U, and V. So where does the W come from? Now you are making that matrix. So W is equal to 2U. Do we have the matrix U? Of course. So we have the matrix U. So what do we do with that matrix U? What should I do with that? Should I just write back U and then that's W, matrix W? What should I do with the matrix U now to get my matrix W? What should I do? Any takers on that one? What will I, oh, times, I think you really meant to say times it by 2. All right. So what does that mean when you say times it by 2? Does that mean I should just multiply one number by one element by 2? What does that mean? What does that mean to you? Just 2 by 1 and that's all I do? Multiply all the elements, all right? Multiply all the elements in that matrix. So that's what we're gonna do. So 2 times 1 gives us 2. What is 2 times negative 5? What does that give us? 2 multiplied by negative 5. 2 multiplied by negative 5. What does that give us? 2 multiplied by negative 5. All right, negative 10. 2 multiplied by 6. 2 multiplied by 6. Okay, and 2 multiplied by 4. All right, good. So that will give us that value. Now, let's see if you will pick up no. So what element in W, in matrix W, is in the first row, second column? What element is in the first row and the second column? First row, second column. So what elements are in the first row? You might ask yourself that first. What elements are in the first row? 2 and 12. And what element is in the second column of that first row, right? So that's actually 12. Now, let's look at another one just for checking. What about the element that is in the second row, first column? Second row, first column. What element is in the second row and the first column? All right, negative 10. Do I have anyone else say negative 10? All right. 2 is better than none. All right. All right, good, fantastic. Now, the other question, it says you want to use T and U, sorry, to show that matrix multiplication is not commutative. In other words, some persons might say or use something simpler to understand what is commutative. Commutative property, you would have done that in literally 7th grade, 8th grade, and you do it again probably in 9th grade just for doing it sake to some extent. But now you see how it's crucial to actually remember that. Now what it means is that if I multiply matrix T and U, is that equivalent? Well, is that equal to the matrix of UT? So I switched it around. So in other words, it's like saying I have 2 multiplied by 1. 2 multiplied by 1 is the same thing as 1 times 2. It gives me the same result. All right? So some persons will say they turn around the numbers, and once they get the same result, that is what we call commutative in the long and short of it. All right? So that's what we're gonna do. All right? So that's what we're gonna do. We did vector TU, No, we didn't. We just got the product of that, state the matrix product of that. So let's multiply. So remember that we got TU again of -3, 16, -11, and 36, respectively. So we're using what we got from the previous question in part 3 to assist us with what we're going to do next. So we need to find the vector, well, the matrix product of UT. I'm getting ahead of myself. So therefore, we need to calculate that matrix product of UT. So we ask ourselves, are these two matrices compatible? When I multiply U by T, matrix U by T, are they compatible? Yes, no? How do you know? Can anyone tell me? How do you check if it's compatible? Does anyone remember? Is it compatible? Yes, no? All right, so let's check. You think so? All right, the matrix U. What is the matrix U? What is the order of matrix U? What is the order of that matrix, the U? We're just checking for compatibility. 2 by 2. All right? Oh, 2 by 2. Right? And what is the order of the other matrix, the matrix T? What is that? All right, somebody said it's the same, switch it around. So what is the order of matrix T? It's also a 2 by 2. So we use the inner dimensions, and sorry for the bad handwriting, to check compatibility. So they are compatible because the number of columns in the first matrix is equal to the number of rows in the second matrix. All right? And now that's what we check first, and we know that they're compatible. So that's the first thing that you want to do, whether you're adding, subtracting, or multiplying matrices. All right? You want to check if it's compatible. So let's multiply. And again, row by column. So 1 times 2 added to 6 times 4. Now, what do you think I'll multiply the -5 by? What should I multiply the -5 by? What digit will I multiply the -5 by? Can anyone tell me quickly? All right. 2. And I'll multiply, good. So yes, 2. And the 4 I'll multiply by 4. Now, are we finished right there? No, because we have our second column in the second matrix. So that's when we know when we stop. We should actually stop to some extent. All right. So we have 1 and 3. So we're going to repeat this. So we remove the brackets. We write it back technically. And we have 1 times 1. So row by column. So 1 is multiplied by 1, and 6 is multiplied by 3. And the same thing goes for the other as well. All right. So UT is equal to this. What is the final value for this matrix product of UT? What will I get? 2 plus 24, what does that give us? Quickly, let's do some addition quickly, computation. 2 plus 24. Mental math, 2 plus 24.
26.
26, all right, good. I'm hearing some voices, fantastic. 1 plus 18.
19.
19. What is the value of the element that would be in the second row, second column? What is the value of the element in the second row, second column? What do you think about that? What is that value? What is the value of the element that will be found in the second row, second column? What would that be? So that's -5 added to 12. And what does that give us? -5 added to 12 gives us what? -5 added to 12. What does that give us?
17. 7.
7. Yes, you corrected yourself. That's good. Fantastic. Self-correction is always good. All right. So the final values are elements, I should say, in this matrix. 26, 19, 6, and 7. All right. So T and U, matrix TU, is not equal to the matrix of UT, the matrix product of UT. So even if you see one element that is the same thing in each of the matrices that we multiplied, you need all of the elements to be the same, all right, for it to be commutative. Okay? Is everyone okay with that? Even if it's one element, it is not commutative. All of the elements in both matrices must match up with their positions. So just like the -3, it must match up to -3 on the corresponding matrix product. And the corresponding one is what? What is the corresponding value to -3 for that matrix? So we have the -3. What is the corresponding element in matrix UT? Can anyone tell me? First row, first column. What element is in the first row, first column for matrix UT? Matrix UT. First row, first column. What is that element? You're saying 19? No, it's 26. So is -3 equal to -20? Sorry, is -3 equal to 26? No, it's not. All right? And you can also check it for the others, but obviously we should be able to see that the elements, all of the elements are not the same. All right? So 16 is equal to 19, and we know that's not true. So this is how we also check. So the matrix product must be the same value. All right? And remember that you could say, all right. Yes, we will get to see when matrix multiplication is said to be commutative. All right? So let's move. And again, you can always take the screenshots of this, the working out, or you can always go on the YouTube in your own time and try to get what's happening if you don't already understand what's happening. All right? So the last one. So we have matrices PQR, and they're given as follows. And then we need to find the constants A, B, and C. So we are given matrix P added to Q, and it's equal to R. Matrix R, sorry. So find the values of A, B, and C. So you write the values down. And then we want to check. We want to check if they're compatible. We can just add matrices, right? So we check the compatibility of all of them. So they must be the same order. So what is the order of P, Q, and R? Are they all the same? P, Q, and R, are they the same? Yes, no? And what is the order? For matrices P, Q, and R, what is the order of all three matrices? Are they the same? 2 by 2. So yes, we can actually add them. Yes. So let's add. Now, what do you think I'll add to 3? Let me just write down the 3. What do you think I'll add to 3? Let me just circle the 3. What should I add to 3? 1.
1, sir.
And then, yes, 1. And what is it equal to? What is it equal to? Okay, C. All right, on the right side of the equation. So again, you want to make sure that you have all of the positions lined up. So the first column, you match it, or the position of each of the elements in the matrices, and that's how we show equality in that regard. All right? So let's just go through. All right? So you would have checked the compatibility, and we would have identified corresponding elements. So let's go. So we add 3 plus 1, -9 plus B, A plus -4, 7 plus 1, and all of that is equal to what you're seeing on the screen right now. So what do you think the value of C is? Based on my last line right here. What is the value of C? What is the value of C now? How do I find the value of C? What is the value of C? What is the value of C? So we match the positions again. So 4, I circle the 4. And what is it equal to on the right side of the equation? In other words, matrix R. It's equal to C. What about 8? This will be done later, but what is 8 equal to on the other side? 8 is equal to what element? What position is 8 at? And we compare it to the one on the other side. So what is 8 equal to? What is 8 going to be equal to on the right side of the matrix? Yes, 8. Yes, you might think that is awkward to say, but it is 8. All right? So again, once we identify the corresponding elements, that's what we're gonna do. All right? So let's just do that. All right, so now you're gonna see, let's match. So 4 is equal to C, right? So I have a little table thing with my solutions. So 4 is equal to C. Now let's continue. -9 added to B is equal to -3. That's the corresponding elements on left side and right side of the equation. So obviously we can't leave this as our answer. We need to solve this linear equation. So what do we need to do? We need to get rid of the -9, some persons might say, but we're really using the additive inverse. That might not be a term that we use a lot, but that's the actual correct term that we should be using in math. So we do the additive inverse. In other words, the opposite of, well, the inverse of -9 is going to be adding 9 on both sides. So that's what we're gonna do. So we add 9 on both sides. So -9 added to 9 gives you what we call 0, all right? And we do that to both sides, so we get B is equal to 6. And you always want to check back your work. When you get -9 added to 6, what does that give you? It gives you -3. All right, same thing, A minus 4 is equal to -4. We do the additive inverse of -4, which is adding 4, and that's what we do to both sides, and A is equal to 0. Again, check your solutions. Don't leave it up to chance. So anywhere we see A, we will write 0. So we're substituting. So 0 minus 4 gives you -4. All right? And lastly, 8 is equal to 8, as was said earlier. So we found the values of A, B, and C. So that is our little icebreaker. Just in case you weren't here at the first matrices session, and we continue. So the first one is the determinant of a matrices. So you want to evaluate the determinant of a 2x2 matrix. Now, you can actually find the determinant of other matrices, like a 3x3, etc. But that is for CATE mathematics, if you're going to do CATE mathematics. All right? So for us, for the CSEC syllabus, we only use 2x2, right? To find the determinant of and the inverse. So what is the determinant of a matrix? Now, every square matrix can be associated with a real number called its determinant. So what does that look like? So for a 2x2 matrix, we have matrix A, and we have the elements reading from top left going down. So A, B, C, D. And this can be written as the determinant of A, which is 2 vertical lines. The matrix A is between 2 vertical lines. So if you see that, it means that you're finding the determinant. Another way you could see it is det A, all right, DET, and then you have the matrix that you're finding the determinant of. Another way you could see it is, again, the vertical lines, and you have the elements of the matrix that you're referring to. In other words, how do we calculate the determinant? You might see AD minus BC and wonder, how did I get that? How did we get that? Now, what do we say? We have the leading diagonal, which you're seeing right now, which is in the color red. So we have AD, we multiply AD, we minus that from the what we call the non-leading diagonal, which is in blue. So that's AD minus BC. So again, the leading diagonal. How do we identify the leading diagonal? It's the top left to the bottom right. So A and D. A is in the top left and D is in the bottom right. So that's how we identify the leading diagonal. And that is always true. All right? And then we have the non-leading diagonal. All right? So the determinant, you might ask, why do we need to learn this? So the determinant is really helpful for us to get the inverse of a matrix. And this gives us more information when we are solving what we call a systems of linear equations. In other words, simultaneous equations. So you have different ways of solving simultaneous equations. You have a matrix method, which we will get into in the next 40 minutes or 30 minutes or so. So how do we calculate the determinant again? We find the difference between the products of the leading and the non-leading diagonal. So that AD minus BC, that is what is being said right here. So we have matrix B, and it is given by 8, 15, 7, and -3, sorry. What would be my leading diagonal? What are the elements in the leading diagonal? Can you tell me? You can open your mics and speak, or you can literally just type it in the chat. What are the elements for the leading diagonal? Any takers for that one? 8 and -3. So we multiply those values. What is 8 multiplied by -3? 8 multiplied by -3, what does that give us?
-24.
All right, good.
24.
All right, what about BC? BC, the product BC is what we call the non-leading diagonal. So what do we multiply and what is our value? When we multiply the non-leading diagonal elements, what do we get? And yes, you can use the calculators. I did say you can use the calculators.
105.
All right, 105. Now, remember that there is a minus sign. That is why they say difference. So we have -24, right? Minus 105. Now, what does that result give us for the determinant of B? So again, once you see the B, the matrix B, and you see the two vertical lines at either sides of that matrix B, it means the determinant. And we get, that's a -129. Can anyone second that? Can anyone second that value that we got for our determinant?
Yes, sir.
All right, good. So, and next thing, ensure that you're actually using the calculator that you'll be using in the exams, whether that be a mock exam or the exam that you'll be sitting next year. Don't rely on your phone calculators because obviously you won't be using your phones in the exams. All right? So practice with your calculators from now so you can get the ease or the hang of it. So determinant of B is equal to -129. So thanks for that. Now what about this? Let's see if anyone can give me the value of this determinant of this matrix quickly. What is the determinant of this matrix? And again, it is the leading diagonal, the product of the leading diagonal minus the product of the non-leading diagonal. So quickly, let's see who can give me the answer first. A boy or a girl? Anyone? The final answer, the final answer. All right, Javon, final answer. So 1 times 4, then what do you do? All right, I'm
So
seeing
would that be
-2.
-2?
All right, and I guess I can third that now, but yeah, -2. So 1 times 4, as Javon said, and then we have 2 times 3, which gives us a 6. So it's 4 minus 6, and as Shanaja said, or Cameron Clark said, it is indeed -2. What about the determinant of this matrix? Quickly. So the boys, girls are
So
on
would that
one.
be 4? So would that be
4?
4?
4 or -4? Just ask it.
-4, sir.
+4.
+4 or -4?
+4.
Positive.
All right, so I don't have anybody to give that point to. But yeah, so -5 times 0 is 0. Then we have, let me just write it down, just in case you might not be seeing it. So you'll have -5 times 0 is 0. You have the minus sign. What is 2 times -2? That's -4. And you might ask yourself, oh, a -4 the answer, man. But remember that there is actually a minus sign in front of the brackets. So 0 minus -4 is actually +4. All right? So we have to work on our integers and the computation of those integers. So it does give us 4. All right? So always check back your work. Don't leave it to chance. What about this one? Quickly. Let's see if the girls can take it or the boys will draw the game. So that's 1 to the girls.
0, sir. 0.
0? All right, 1. Let's see if that's true. So 1 times 4 is 4. 2 times 2 is 4. So we have 4 minus 4. And that is indeed 0. All right. Are we all on the same page? Yes, no?
Yes.
Yes,
All
sir.
right, cool.
Yes, sir.
All right. Now, what can you say about the values of these determinants? We found 3 determinants. What can you speak of? What are you seeing? You see anything that's worth noting when you got our determinant values? Do we see anything worth noting? Compare all 3. And I would have mentioned integers, so that is something that you can use to some extent, but not to that extent. All right, it's fluctuating, okay. All right. All right, you said fluctuate. All right, let's see. So we have positive or negative values that we got for a determinant, all right? So whenever we get positive or negative values of our determinants, that means we call it, or the term that we use is non-singular matrices. Now, this is not singular or plural in the English language, okay? This is a math language. So don't think the opposite of singular is plural for mathematics, all right? This is the math language that we use. So positive or negative values of the determinant are what we call the non-singular matrices. Now, what about 0? 0 is not a negative or a positive number. So how would I say anything? Can I say anything about that? So when I get a negative or a positive number, it's a non-singular. So what would when I get 0 be called? It is a singular matrix. All right? So whenever you get your determinant to be 0, it is singular. Not by itself, but it's a term that we use in mathematics called singular matrix. All right? So don't confuse them with the English language. All right? Now determine quickly. Let's see who can give me the values very quickly. The first one, first matrix, you want to determine if it's singular or non-singular. Again, boys versus girls.
0. Non-singular.
Non-singular?
No,
Which one?
singular.
Singular? Okay. Technically, I can't give you that. So 8 times 1 gives you 8 minus 2 times 4, which is 8, right? So that is indeed singular. What about the second one?
Non-singular.
Non-singular? All right. So
Yes,
2
sir.
times 5 is 10 minus 3 times 1 is 3. So we have 10 minus 3, which gives us our lucky number 7. What about the last one? What about the last matrix? When we find the determinant, what will it be?
Non-singular.
Non-singular. The girls are taking it. All right. So -1 times 9 is -9 minus -2 times 4 is -8. So if I'm talking too fast, let me just write it. -1 times 9 is -9, sorry. All right. Then you have the minus, -2 times 4 is -8. And as I always tell persons, use your brackets, especially when you're going to put it in your calculator, because not all calculators are the same. So this really gives you -9 added to 8, which is -1, which we say is a negative value. And that is how we get it to be non-singular. So for the persons in the back, that's how we get it. All right. So let's go. Now, you won't necessarily always see a lot of numbers. You might see a little expression. You might see algebra being used. All right. So don't get too comfortable with just numbers. You might see unknown or variables being used. So we want to calculate the value or the values of x for which the determinant is 0. What is the determinant? Is it based on the question? Is the determinant a singular matrix or is it a non-singular? Is this matrix of M a singular matrix or a non-singular matrix? Which is it? Singular, all right? And we said because the determinant is 0, determinant of M is 0. We say that is singular, all right? All right, let's continue. So what are we going to multiply? Leading diagonal. Identify the elements of the leading diagonal. What are those elements?
And 3.
Repeat, Anastasia?
And 3.
Okay, 2x and 3. What is the product when we multiply those two elements? What does that give us? How much?
6x.
All right. And Sadra, just listen to the question. All right. I said, when we multiply the 2x times 3, what do we get? Not the final value that we should be getting. All right. So again, we have our determinant. All right. We have our determinant formula. Our determinant of M, matrix M, is equal to AD minus BC. Again, AD is our leading diagonal. BC is our non-leading diagonal. So we would have multiplied 2x times 3. That's 6x. And what is 2 times 9? How much does that give us? 2 times 9?
18.
18. So we have 6x minus 18. Do we stop right there? Is that our final answer? Did we find the value of x? You ask yourself that. Did we find the value of x? Yes or no?
No.
No. So what should we do next?
Divide by 6 on both sides.
Divide by 6. Remember, when you have an equation, once it's linear, you should have only one unknown. Now, currently, we kind of have technically 2 unknowns. Do we have the determinant of M? Was that given? What is the determinant of M? What was that given as? Determinant of M? 0. So what do we do with that 0? What do we do with that 0? What do we do with that 0? We substitute it. No, we substitute. So under the determinant of M thing, matrix M, we write or substitute 0. All right? So remember that that was given. So this is what we get. 0 is equal to 6x minus 18. So what do you think is the next step in order to find or solve this linear equation? Because we have one unknown. Oh, what should we do right now?
Can we put the negative 18 over the equal sign?
Is it really going over? The term that we use is additive inverse, but we just say, some persons might say the opposite of negative 18, but all right, so we use additive inverse. So when you say bring it over, you mean literally bring over the negative 18 and we get negative 18 on the left side? That's what you're implying? What are you
When
actually
it goes
implying?
over, it's gonna be positive 18.
So do I do that on one side or do I do it on both sides? Which one? One side of the equation or both sides?
One side.
One side. Remember, you want balance it now. So you have to do both sides. It's an equation. Whenever you have an equation, whatever you do to one side, you have to do to the other side. So what are we going to do? We're not going to bring it over. We're going to add 18, which is the additive inverse of minus 18. All right? So that's what we're going to do. So we have 0 plus 18. And it's equal to 6x minus 18 added to 18. Now what does that give us? What should I have now? Now this is when you actually say cancel. We generally misuse the word cancel and simplify. So we cancel negative 18 and 18. That gives you 0. All right? So on the right side, we just have 6x. What is 0 plus 18, everyone? What does the crowd say? 0 plus 18 is 18. All right? And it's equal to 6x. So what do you think is the next step? Should we add, multiply, divide, or subtract? Which one of the
Divide.
operations will we do now?
Divide.
Can anybody tell me why we divide? Can anyone tell me why we divide?
Because you're trying to get x by itself.
Okay, besides that, why we divide? It's really called a multiplicative inverse.
Because you're doing
divide.
the opposite.
Yeah, technically speaking, yeah. The opposite of multiplying is dividing. Remember that the 6 is being multiplied by the x. So always remember that. So this is how we get the divide both sides by 6. So what will x be? What is our value of x?
3.
3. Just one answer we get, right? X is equal to 3. So don't be confused with what the question is asking you. The question said you might get value or values. All right? So in this case, we got a value. So the value or a value is going to be 3. So what if x was 4? Would my determinant still be a singular matrix? Ask yourself that. if I got any other value besides 3 for this matrix, would my determinant be called a singular matrix? Ask yourself that. And you can always work it out too, you know. If I got any other value besides x is equal to 3, would my determinant of matrix M be a singular matrix still? Can anyone tell me? Or can anyone instruct me to use a number or something? Would it be a singular matrix still? Yes, no, maybe?
No.
All right, so let's check. You always want to check. So let's say x was 4, all right? So I could use this line right here and multiply. So we multiply 6 by 4 and we minus 18. 6 times 4 is 24 minus 18. What is my determinant? 6. So if my determinant is 6, is that a non-singular or a singular matrix? It is a non-singular. So the question doesn't necessarily have to ask or give you that it's a singular matrix. They could say, give me the value of x when it is a non-singular matrix. So what would we do? We would just do the same singular matrix method, like what we're doing right now, but we will write x is not equal to 3. So any values of x can work for this matrix that we're working out to be a non-singular matrix. All right? So that is something, our food for thought as well. All right? So 2 things that we need to find the inverse of a matrix. We need the determinant, which we got earlier, which we found earlier, and we need to find the adjoint. So the next thing is going to be the adjoint of the matrix. So let's go. So to find the adjoint of a matrix, we would interchange the elements in the leading diagonal. What does that mean? You identify your leading diagonals, then you change the values. All right? So we'll go through examples of that as well. And then for the non-leading diagonal, we keep the position and change the signs. In other words, we're multiplying by -1. And then this would be called the adjoint. All right? Yeah, you can say flip, or some persons will swap as it pertains to the leading diagonal. All right? But I just use the word interchange. So what do you think would be the adjoint of this matrix? What do you think would be my new leading diagonal? What would be my new leading diagonal when I'm finding the adjoint of this matrix B? Can anybody tell me the values? Okay, 10 and then 5. All right, what about my non-leading diagonal? What would be my elements? Well, the top right. Okay, so all right, good. You said it like that. Okay, -4, -8. Now let's look at it visually, because I just basically said it. All right, so visually, this is how it would look. All right? Now, this is the adjoint of the matrix B. Now, what happened? The leading diagonal, if you look at the question, matrix B, it was 5 and 10. But what did we do? We interchange, or another person might say we swap, right? So we swap the leading diagonal. So the positions change. All right? While the non-leading diagonal, you notice you still see the digits technically at the same place, but the digits are different as they are being multiplied by -1. In other words, you change the sign. So this was a 4 and a positive 4 and a +8, and we change the signs to get negatives. So that would be our adjoint of matrix B. It might look simple, so don't do an overkill with this one. All right? So the next thing is what we call the inverse of the matrices. So remember that we needed 2 things. We needed to find, oh, okay, I get you. All right, hurry up quickly. And you can always go on YouTube just in case you can't log in again. So to find the inverse of a matrix, remember that we said we needed 2 things, the determinant and the adjoint. So technically we did a lot of those, but let's go a bit more into it. Now, the question that you might ask, can we divide matrices? And what is that answer? Have you ever heard anyone say, oh, let's divide these matrices? Can we actually divide a matrix? In theory, I would say. Can we? Yes, no? Remember the operations? Add, subtract, multiply, divide. All right, so let's see. So operationally, it is not possible to divide matrix, right? But we can instead multiply the matrix by its inverse, and this will give us the same results. So we therefore do not need to divide if we know the inverse of a matrix. All right, and this question, I will be asking this question in the next probably 20 minutes or so. Does every matrix has an inverse? Remember, when you have the determinant, we have either a singular matrix or a non-singular matrix. All right, so again, that question will be asked in the next less than 20 minutes. Does every matrix has an inverse? All right, so let's go. So let's take a little deeper look on how we actually get the inverse. So the terms that we generally use, we kind of use them loosely, but the correct term is either multiplicative inverse or the reciprocal. So in other words, if you have A by itself, you might say, oh, what is the reciprocal of A? You might say, the reciprocal of A is not A, that, sir. So it is actually 1 all over A. So in other words, the reciprocal of A is that value. So let me just point it out. So A, okay, sorry. So A, sorry about that, that might look like a 9, but A is the same thing as A all over 1. So when you reciprocate this A all over 1, it gives you 1 over A, all right? In other words, it's the multiplicative inverse. Now what happens when I multiply A by its reciprocal? It gives me, as what you're seeing on the screen, 1. Not cancel, it is 1. A into A does not cancel. It is simplified to give you 1. So do not think it's canceling. Canceling gives you 0, or what we call 0 pairs. So pay close attention to what you're saying and make sure you're not confusing anyone if you're actually educating one of your friends or so, or helping somebody out. All right? So what would be the reciprocal of, I know it's on the screen, but what would be the reciprocal of 2/3? What would be the reciprocal of 2/3? Using the same notion that you're seeing on the screen right now, what would be the reciprocal
That'd
of
be
2/3?
3 over 2.
All right, we don't really say 3 over 2, but 3 halves. All right, so fine. So that's
Okay.
3 halves. All right. And what happens when I multiply them? What is the result? When I multiply the reciprocal of 2/3, what do I get?
Would that be 1 over
1.
1, sir?
Well, technically 1, but yeah. So 1 over the 1 is the same thing as 1, okay? So 2 into 2 goes 1, 2 into 2 goes 1, 3 into 3 goes 1, 3 into 3 goes 1. All right? Is everybody clear with that? Any questions? No?
No, sir.
All right, cool. So again, all of these things you might say, oh, this is more work and all that. But once you have the basics, the knowledge and the why, instead of just getting a formula and just say, oh, let's just rock with this, you can see that this is actually practical and you can use it in your future questions that you'll be getting. So the product of a number and its reciprocal is equal to 1. And we call that 1 multiplicative identity. All right? So that's what we call that 1. So you might say, okay, let me just write this down. So you see A, you see matrix A, right? Are we all seeing matrix A? Are we all seeing matrix A?
Yes,
Yes,
sir.
sir.
Now, how would I call this one? How would I say this? The one that I just circled, the second one. How would I call this that I'm seeing right now? Any takers? Anyone want to try? How would I call this matrix? What would I call it? I'll give you two options. Should I say A to the negative 1? Or should I say the inverse of A, matrix A? Which one?
The
The
inverse of
inverse of
matrix A.
matrix A.
The inverse of matrix A. So again, this is not indices when you have a base raised to a power. So again, you might think that thing at the top and say, oh, it's a negative 1 power. No, it's not. So again, certain things might mean different in have different meanings in different areas or topics in mathematics. So what about the one over here? What is this I called? Do we know a term that we can call that I? We say matrix I. What is it really? What is that? It's called matrix, the identity matrix. All right? How do we know that this is an identity matrix? The leading diagonal is always going to be 1. So again, the leading diagonal is always going to be 1, and the other elements are going to be 0. All right? So that is how we can also pick up on what that is. So it is an identity matrix. So when you multiply the square matrix, which is matrix A, by its inverse, we get what we call an identity or a unit matrix. So this is what we do instead of saying, oh, we divide the matrices and get identity matrix. We actually multiply the inverse of the matrix. Well, the matrix by its inverse. All right? So that's what we actually do, and we will always get the identity matrix. All right? And again, you'll have to check the compatibility to see if they can be multiplied. So we have given that matrix A, I, and B. We have those values. And I want the boys to the AB, matrix AB, the product of AB. Boys will do that. And the girls will do matrix BA. I'll give 2 minutes, give or take. All right, so 2 minutes to do that. Two minutes. And then we'll check it to verify. So you're doing matrix AB and BA. All right, less than 70 seconds remaining. All right, so what did we get for AB? What did we get for BA? AB, matrix AB and matrix BA. Did we get any values? Anyone, boy or girl? Any individual? A, the product of AB, matrix AB. All right. So you should get, when you multiply matrix A by B.
Sir.
Go ahead. Yes.
I'll give it a try. I got 2, -1, and then at the bottom I got 1 and +4.
All right. Now that's for AB.
Yes, sir.
All right, let's just check because we're all humans. Just checking quickly. So we have 2, we have 2, -1, 1, 4. That's A. And B is going to be 1, 1, 1, 1. All right. So row by column. So 2 times 1 gives you 2, right? 2 times 1 gives you 2. -1
Yes,
times
sir.
1 gives you negative 1,
1.
right? All right,
Yes,
let's
sir.
continue. So this row now will be multiplied by the same column that we just mentioned. So 1 times 1 is 1, right?
1.
Plus, oh, I forgot to put this plus right here, just in order to keep consistent. 4 times 1 gives you 4. All right? So we're finished
Yes,
with
sir.
that column in the second matrix, so we go on to the second column in the second matrix. So we do the same thing. 2 times 1 will give you the same thing, all right? Because the value is the same, which is 1, all right? So technically, it does give you the same value. So 1 plus 4. And this is how you get 1, 1, 5, 5, all right? So you have to check your work and make sure you have the right thing, all right? So it might be a error that you did or whatnot, but you should be able to see the mistake, or if you made a mistake, all right? So always check your work.
Yes, sir.
All right, and the BA would have been 3, 3, and then AI, not that AI, artificial intelligence, but matrix A times matrix, the product of matrix A and I. So this would have given you 2, -1, 1, and 4. And when you multiplied I by A, you would also get the same thing. Now, what are you seeing? What are you seeing based on the results in part 1 and part 2? Are you seeing any differences, similarities when you got the products of AB and BA and compare that to the products of AI and IA? The matrix products, of course. Are you seeing any similarities, anything different? And what is similar,
Yes,
what is
sir.
different? Yeah, go ahead.
For A, B, and BA, they have different matrices, or I don't know if that's what you call them, and for IA
Elements.
and
Elements,
for
yeah, you can say elements, yeah.
elements, and for AI and for IA, they have similar elements.
All
Or
right,
the
they have
same
equal,
element.
yeah, the same equality, yeah. So, do you see anything else that is worth noting when you're multiplying them, as it pertains to the matrices that we multiplied? Anything else that you're picking up? So remember that AB. So what does this show you? So let me just write it quickly. So AB. So technically, what we're saying is that AB is not equal to BA, right? Are we all agreeing with that?
Yes, sir.
And
Yes, sir.
AI is equal to IA. So what does that tell you? Remember, we would have done a lot of these AB is not equal to BA thing. And there is something different now with this second one. What do you notice that is different with this one? Good afternoon, by the way. So what do you notice with difference between this and the top one? Again, the I is our identity. So when I multiply an identity by a matrix, or when I multiply the matrix by the identity, the elements are the same, right? So what does that really show you? It shows you that when you're multiplying by the identity matrix, you will have it being a particular word that was said earlier in the first part of the session, but it is commutative. And is this only when that happens? Is that only commutative? At that stage, when you multiply the identity by any matrix, it's equal to the identity multiplied by the matrix, or vice versa. So that only happens when you have the identity matrix being multiplied. All right? So in technicality, I wish I could have more to say. I mean, more time. But in practicality, it means that the identity matrix for a multiplication, whenever you multiply a matrix by another, it will always be the same matrix. So what this is saying is that there is only one case when matrix multiplication is commutative. And this is the case when you are multiplying the matrix by the identity matrix. All right? And that is the only case when matrix multiplication is commutative. All right? Is everybody with me with that? Is everybody with me?
Yes, sir.
All right. So again, you can take that screenshot, and then let me just write that AB is not equal to thing again. So AB is not equal to, sorry for the bad handwriting, my penmanship is poor, and AI is equal to IA. All right? So that is only when matrix multiplication happens. It's commutative at that stance when AI is equal to IA. So it doesn't have to be A, can be another matrix, as long as you must be multiplying it by the identity matrix. All right? So let's move. So the inverse of a matrix, so you have this matrix, you have matrix A, right? So matrix A, when I multiply both sides, remember, when we multiply a matrix by its inverse, we get what we call an identity matrix. And remember that this, what you're seeing on the screen right now, is commutative. So A, matrix A times its inverse, and even if you switch it around and have the inverse first, the inverse of the matrix multiplied by the matrix, you will always get an identity matrix. All right? In other words, it's like saying 1 times A is technically gives you back whatever you would have gotten. All right? So 1 times A is always A, and the same applies. So anything multiplied by the identity matrix, any matrix multiplied by the identity matrix will always give you the identity matrix. So we would have done that. So again, this is a 2x2 identity matrix. So we have this one, just a concept check. So we have 2 matrices, A and B. So our matrices A and B inverses of each other. So how do we know that they are? So we have matrix A and matrix B. Now, you might say, oh, let's multiply them and see what we get. So when we actually multiplied it, or when we can actually multiply it, matrix A multiplied by B will give us, what is this matrix called? What is 1001 called? What is that matrix called? What is the term used for that matrix? Anyone can tell me?
Identity matrix.
Identity matrix.
Identity.
So let's see if it happens when you multiply B by A. So yes, it does actually happen as well. It gives us an identity matrix. So we need to prove it a bit further to say, oh, are these actually inverses of each other? So let's also check. So this case, or this scenario, will give you the identity matrix when you multiply AB by BA. And this is a special type of proving, all right? Again, this is concept check. So multiplications are also commutative. So we have to be very careful. We actually have to check it, multiply it, and not just leave it up for granted, all right? Okay, so that goes right there. So AB, matrix product of AB is equal to an identity matrix. So what are we saying? That the B is the inverse of A, and A is the inverse of B, as you would have seen earlier in the matrix multiplication, which was actually pre-done already, all right? And it would have given you the values. But you can always do it in your own spare time to just confirm it for yourself as well. But those are the values that we'd have gotten, which are the identity matrix. So let's take a closer look as it pertains to how we get this 2x2 inverse. So let's see. How else can I write 0.1, 0.1, negative 0.7, and 0.3? Is there another way I could write it? Instead of writing it as a decimal, is there another way I could write it? How else could I write
as a fraction?
Yeah, but what would that fraction be? 0.1 or 1/10, I should really say. So that is 1 all over, well, 1/10, right? So that's how we write as a fraction. So as you would have said, a fraction. So that's similar. So matrix B, you see the fractional aspect of it, and above you would have seen the decimal. So are those two the same? Are those two matrices the same? All right, they are the same, all right, because it's the equivalent in a fraction form. So is there anything that you think is a common factor in matrix B? Does matrix B have a common factor? Is there anything that they have similar in all elements? Besides saying their numbers or digits, by the way. Anything in particular that they have in common, a common factor?
Yes, sir.
Yes, what is that common factor?
Would that be 10?
Okay, 10. Numerator or denominator 10?
Denominator 10?
So what would be the fractional part of it? It would be 1/10. All right? So, as you would have done in something that we call factorization, right? We can take out the highest common factor, which is indeed 1/10. So we factor out the matrix B by using the common factor of 1/10. Now what will that give us? It will look like this. So 1/10 is equal to the matrix 1, 1, -7, 3. Now compare it to matrix A. Compare that matrix B now that we have. Compare it to matrix A. Are you seeing any similarities? Anything worth noting? So we're comparing matrix B that we're at right now with matrix A. This one at the top. Do you see any similarities? You pick out anything worth noting or
Yes,
worth
sir. They
noting?
are the same, but it flip.
It slip.
Or
All right.
it's
What is this?
something
What about
of-
this part? This one right here. What is that? What is the name for this? And compare it to the matrix A. What term is this really? Nothing?
Would that be an
A is
identity?
No. Check it again. Let me
would it be an
erase.
inverse of
Let me
something?
erase. So compare again. Compare this part of B, matrix B, with A, and see if you notice anything that you would have done earlier as it pertains to determinant and adjoint. Compare those two that I just circled. It's what? It's actually the adjoint. So that little part right there is the adjoint of A. So you swap the leading diagonal, which is the 3 and the 1, right? And you see the 1 and the 3. And the non-leading diagonal, the signs will change. All right? So that's what's really happening. So what about, so that's the adjoint of matrix A. What about the 10? Look at the 10 that you have in the denominator and compare it to a term that we would have used earlier. Remember the terms that we used earlier? Determinant and adjoint that we found. So if this is the adjoint, what do you think the 10 would be saying to us? What do you think the 10 is saying to us? It is saying that it is the determinant of A, matrix A, of course. How do you know it's the determinant of A, matrix A? 3 times 1 is 3 minus -1 times 7, which is -7. So what do we have? 3 minus -7. And what does 3 minus -7 gives us? It gives us the 10 that we have right here. All right? So that is the determinant of A. So that's how we actually got the inverse, or that's how we manipulated the inverse. All right? So they are indeed inverses of each other. So this is how the formula comes into play of the 2 by 2. So this is the general form. So you have a matrix, whatever that matrix is named, and it's normally a capital letter, by the way. So A is not common A, it's a capital A. So that informs you that it's a matrix A. And then we have the inverse of A, not A to the -1, and it's equal to 1 all over AD minus BC, which is our determinant. So in other words, the reciprocal of the determinant multiplied by the adjoint of the determinant. So the question I asked earlier, does every matrix have an inverse? What do you think about that now? Does every matrix have an inverse? Does every matrix have an inverse? Does every matrix has an inverse? And it's literally 23 minutes after. Does every matrix has an inverse?
No,
What do you
not
think about
every
that?
matrix has an inverse.
So which one not have no matrix? Which one not have no what you call it now, inverse. How do you know? How do you know? How do you know? Again, the two types of
Because
matrices
one of
when you
them
have.
is singular and non-singular.
Okay, so when can we find inverse? When it's singular or non-singular? Which one? All right, let's
Non-singular?
non-singular. All right, let's check. Let's check. I want you to put 1 all over 0 in your calculator and tell me what you get.
Sir, can you repeat?
Sir, undefined.
Okay, 1 divided by 0, 1 over 0. That's what I asked. It gives you undefined, right? So what this is saying is that 1 all over the AD minus BC. So when you have 1 all over 0, in other words, the determinant is singular, then you do not have a matrix inverse. So this is why the young lady would have mentioned non-singular. So you can only find the inverse of a non-singular matrix. So this is how crucial the determinant is. You don't even have to waste all that time and find the adjoint. Once you find the determinant and the determinant is not 0, then you can find an inverse of that matrix. It might sound simple, but you have to appreciate that aspect of it. All right, so we can only find the inverse of non-singular matrix. Okay, is everybody on the same page? So this is how crucial the determinant is.
Yes, sir.
So non-singular. All right, so given that we have matrix A, 4, 3, 2, 1, we need to find the inverse of A. So the first thing that you might want to do is write down a little general form. So you have the reciprocal of the determinant of A multiplied by the adjoint. What is the determinant? What would be the value of the determinant of matrix A? What would I multiply? And what would be my final value? AD minus BC, 1 all over AD minus BC, the reciprocal of the determinant of A. What would I have? What would be my determinant for matrix A? Any takers on that? What would be my determinant for matrix A? What am I multiplying?
Sir, would you cross multiply, meaning would you multiply the 4 times 1 and then the 2 times 3?
Yeah, but don't use the term cross multiplying. Cross multiplying is an American phrase, okay? We actually do
Okay,
the
sir.
multiplicative inverse. But I get what you're saying, but that's not the cross multiplication that you're referring to. But I understand what you said. So multiply the leading diagonal, which is a 4 by the 1, minus the non-leading diagonal, which is a 3 by the 2. So how do we get the adjoint? What is the adjoint? What would be the adjoint be? Oh, it's the other way around, Javon. What would be the adjoint? What would be the adjoint? The adjoint. What would I have? What is the adjoint? You interchange the leading diagonal elements, which are 4 and 1, and then you keep the position, but you change the signs of the non-leading. So that gives you 1, -3, -2, and 4. So on to the determinant. What is 4 minus 6? What does that give you? 4 minus 6, what does that give you?
2.
2, you sure? 2, positive 2, negative 2, which 2?
Negative.
Negative
Negative 2. So technically, person say when you see the smaller number at the start compared to the other one, it will give you a negative value. All right. So 4 minus 6 is going to give you -2. Now, are you finished right there? Is that our inverse? Is that our final answer? Is that our inverse? Should I leave it as that? Or should I do something else? Is that our inverse of matrix A? No.
Yes, sir.
Okay, so what should you do? What should you do to make sure that this is the last step? So the -1/2 is our scalar value. So again, just like when we had the W is equal to 2U, matrix W equal to matrix twice as much as you, we do the same thing. So each element is going to be multiplied by negative a half. So this is what our result is. So negative a half times 1, negative a half. Negative a half times negative 3, a positive, and that gives you 3 halves. Positive 3 halves. And then you have negative a half times negative 2. Some persons might write negative 2 halves, but it can be simplified, so you simplify it. Whenever you see a fraction that can be simplified, you are encouraged to simplify, all right? Unless otherwise told. So this is a CSEC sample question that we'll be doing. So we have 3 questions to partake in. So we have R is equal to 2, negative 1, 1, and 3. And the first one, it says, show that R is a non-singular matrix. So when they mention that, what are we actually finding? Are we finding the determinant of the matrix R? Or are we finding the adjoint of matrix R? Which is it?
The determinant, sir.
Okay, so how do we find the determinant again? We have the leading diagonal 2 times 3 minus the non-leading diagonal negative 1 and 1. So that gives us 7. So is 7 a non-singular matrix? The determinant of R gives you 7. Is that non-singular or is it singular? Which one is it?
Non-singular.
All right, because it's a positive value. Once you get positive or negative values for your determinant, it will always be non-singular. So on to the inverse. So can we actually find an inverse? Can we find the inverse of R? Is it possible? Is it possible to find the inverse of R based on what we have now? Yes, because we have a non-singular. So we would have multiplied, and again, your final answer will not be 1/7 multiplied by the adjoint, unless otherwise stated. This will be your value. So the elements are 3/7, 1/7, negative 1/7, and 2/7. And finally, the third one, it says, show that when you multiply R,
Sir,
yeah, go ahead. Sorry.
can you?
Yeah, I'm here.
I was asking.
Yeah, I figured as much. Is that cool? Ready? Ready? No? All right, I think you're good. You took a screenshot, I hope. So on to the final one, not the final question, that is. So R, matrix R multiplied by its inverse is always equal to the identity. It says show that. So you can just write down I and think you'll get full marks. You'll have to show the working. So we have the value, the matrix R, and we just found the inverse. So those are what we're gonna multiply. So are they compatible? Yes, they are. It's a 2 by 2. 2 of them are 2 by 2. And the inner dimensions, are 2 and 2. So they can be multiplied. So we would have multiplied them using our technique, rows by columns. All right? And our denominator would be 7. Then we go further with it. 6 plus 1 gives us 7. So 7/7. You don't leave it as that because it can be simplified. So you'll get 1. All right? 2 plus negative 2/7 gives you 0. And over here, 3 plus negative 3 gives you 0/7. And the same for the other one. So it gives you 7/7, 0/7, 0/7, 7/7. So again, you will have to simplify. So 7/7 will always give you 1. 0/7 will give you 0. So this is indeed an identity matrix once you multiply the matrix R by its inverse. So that is indeed the matrix. Any questions on that? Any questions on that, anyone? No?
No, sir.
All right. All right, on to the last thing of the day. Solving simultaneous linear equations using the matrix equation. So you would have probably done simultaneous equations before in your lower years of high school, and you would have done elimination method, substitution method, and even graphically. So there's a fourth method that you can use, but the question will have to dictate to you that you will be using the matrix method. All right? So if the question says solve the simultaneous equation, you are free to use whichever method is applicable or whichever method you are comfortable with. But once it says using the inverse matrix method, you have to use that method. All right? So you're planning a trip, you're an event planner or a trip planner. You want to go to Disney World. So in preparation of this, you want to get adult tickets, adult and children tickets. So at this Disney World trip thing, whichever year this was in, an adult ticket costs $8. A child ticket costs $4. And when you got the total that you collected for the tickets was $280. All right, so adult ticket is $8, child ticket is $4, and you collected $280 worth of the tickets. So the next statement that is given is that you have the total number of tickets that was sold, which is 50. So we have the total number of tickets. So this now, you'll be putting this in a mathematical sentence. In other words, you'll have a equation. All right? So let's see how we get to that equation. So this is how algebra is so crucial in topics in mathematics, and not just for algebra alone. Algebra is all over in mathematics. All right? So we write pair of simultaneous equations. So we say that A, we are going to let A be adult tickets and C be child tickets. Now, that is our variable that we're using, A and C. Now, the question will generally tell you what to use, but most persons generally like to use X and Y. So we are showing you that you don't have to always have X and Y, but depending on the question and how the question is structured. Now, the first equation will represent the cost of tickets sold. Remember that one adult ticket costs $8. This is why you're seeing 8 multiplied by A. And you will add that value to the cost of one child's ticket, which is $4. And why are we multiplying that, adding 4 plus C? Because whenever you find out how many children or how many adults are going, you would multiply it by those values to get the total. They know the total, but we don't. All right? So the total is 280. So our job now will be to find the values of how many adult and children tickets were sold. All right? So this is the first equation. Remember that a simultaneous equation has 2 equations that we need to solve simultaneously. In other words, together. So this is the first equation. Is everybody okay with the first equation of 8A added to 4C and it's equal to 280? Why 280?
Yes,
because that's how much it was sold for. All right, good. Thanks for that. So the next one, the next pair, well, the next equation will be how many tickets was sold. So remember in the statement, it was given that the total number of tickets is 50. So when you put the adult ticket them together with the children's ticket, you will get 50 overall. All right? So it's technically saying, oh, it's in a raffle bag, but you need to sort them out. But you don't know how much adult or children tickets you have. But you know that the total in all is 50. And total generally indicates that we add. So this is how we get A plus C is equal to 50. Is everyone seeing how I got the A plus C equal 50? Yes? No?
Yes, sir.
All right, cool. So we have our 2 equations, which is what you're seeing right now. All right? And you might say, oh, we can do this easy with elimination, substitution, and I even can do it on a graph, but we're doing the matrix method. All right, so we have our two equations. So those are what we're going to use, and we're going to take out or use the matrix equation and then use the inverse matrix method to find the values. So you might be asking yourself, how could you rewrite these pairs of equations? Do you see any similarities with when you have 8a plus 4c and a plus c? Do they have anything in common? In other words, some persons might say a common factor to some extent, but do they have anything in common?
Yes,
8a,
sir.
4c, and a plus c. What do
Yes,
they have
sir.
in common?
The variable c, sir.
The variable c and what? Which other variable? Just c? And the variable
And
a.
And a, sorry.
Yes. So we are gonna see how we actually get that matrix. All right. And yes, Miller, I'm seeing your response in the chat. So this matrix form is what we call AX is equal to B. So matrix A multiplied by matrix X is equal to matrix B. Now what is matrix A, X, and B? Now let's go in depth with this. So matrix A is an M by N, and the elements are what we call the coefficients of the unknowns. So you might say, oh, what is a coefficient again? All right. So we will get to that and pinpoint what we call a coefficient. All right. So matrix X is a M by 1 representing unknowns. So matrix X is the unknowns. So I know you would have mentioned A and C are the unknowns. So those are what we will be using for matrix X, and you'll see shortly. So X is a column matrix. That means it only has one column. While matrix B is a resultant matrix representing the results. So remember that when we got the tickets, we sold $280 worth of tickets, and in total we got 50 tickets. So those will be our matrix B values. And again, you'll see that shortly. So this is our A value. Sorry, matrix A. Oh gosh. This is our matrix A. This is our matrix X, and it's equal to matrix B. Let me just erase that. I don't want to make that look like something it isn't. All right, cool. So is everybody following so far? Is everybody understanding what I'm doing so far? So
Yes,
remember,
sir.
this is just matrices multiplication, right? So let's see. So we want to represent AX. This is AX. Does it look familiar now? Does all of this that we're seeing right here, does it look familiar to having, let me write at the top, 8A plus 4C, A plus C equal 280 and 50. Are we seeing any similarities with what the equations that we have and the matrix equation? Do we see any similarities? So remember that they did say that matrix X is a coefficient of the unknown variables. So the coefficient of A in this first one, 8A, the coefficient of A in this one is going to be 8. All right? And we do the same thing. So you might be wondering, A plus C, the coefficient of A in A plus C is 1. You might be saying, oh, it's 0. But remember that A is the same thing as 1A. All right? And the coefficient of A would be 1. So that's how we get A plus C has a coefficient of 1 and 1 respectively. All right? And I will have to ask everyone to get 10 more minutes. Can I get that 10 more minutes to complete this? As in to complete this last.
Yes, sir.
Yes, sir.
All right, cool. All right, I just want to ask before because it's 2 minutes out. All right, so this is how we write our simultaneous equations in the matrix equation form. So we have our matrix A, which is the coefficient of the unknown variable. And matrix A would be our unknown values. And matrix B would be the resultant matrix. And again, you can always check it, and you can always check your matrix multiplication. Because when we multiply 8 by, as in the first row, by the first column, we get 8 times A, which is 8A. And we add it to 4 times C, which is 4C. And what is all of that equal to? 280. That was our first equation. Then we go to the second row. 1 times 1 and 1 in the second row, multiplied by the A and the C. So 1 times A is A. 1 times plus 1 times C, which is C. And what is all that equal to? 50. And it's the same two equations that we got earlier, but we are breaking it down in the matrix method, or the matrix equation form. So they can say, write these pairs of simultaneous equation in the matrix equation form, and this is what you'll write. All right? So remember that when we multiply the inverse of a matrix by its matrix, we always get the identity. Now, what happens when we multiply the identity by the matrix? We get A. So this is what I was alluding to earlier when I said 1 times A. What do we get? We get A. So when we have the identity matrix of I, matrix I, which is the identity matrix, when we multiply by any matrix, we will get that matrix that we would have multiplied I by. So which is A in this scenario. So this is how we show that the product of the multiplication identity matrix and any compatible matrix is the matrix itself, which was alluded to earlier. So this is where we're at right now. We need to find the unknowns. We need to ask ourselves, how do we find matrix X? How do we find it? Just like when you do equations, you want to balance both sides. So you need to get rid of matrix A. And how do we think we'll get rid of matrix A? Will we divide or will we multiply? What are we going to do? Multiply divided by what? Multiply by what? What are we going to multiply matrix A by to get rid of it?
B.
We don't want it over here. What we're going to multiply it by?
B.
We're going to multiply it by not B. Remember?
8.
The inverse of that matrix. So remember, A inverse multiplied by A, matrix A, will give you an identity. So that's what you actually multiply. So this is why you actually found the inverse, because you're going to use it to find the solutions of these simultaneous equations, well, linear equations, etc. So to keep the matrix equation balanced, as I said earlier, you're going to multiply it by matrix, I know you said B, but I just want to highlight it, the inverse of A. That's what I really wanted to highlight. I know that you were reading from the screen, but I wanted to highlight the inverse of A aspect of it. All right? So in what order would we multiply matrix, the inverse of A and B? What order meaning, oh, should I put B first, then I put A inverse, matrix B first, then A inverse? Or should I put A inverse and then B, etc.? So which one do we put first? We pre-multiply both sides by A inverse. So when we multiply A inverse by, let me type. When we multiply this, we get I. A inverse multiplied by the matrix A, we get I. But when you multiply the inverse of matrix A by matrix B, we won't get I. We'll actually get our answer. Our final answer. Put that to the test. So IX, matrix I, the identity matrix, multiplied by the matrix X is equal to the inverse of A multiplied by the matrix B. So let's do that. So again, we're going from the same question that we did earlier, or that were the tickets question. So we find the determinant and the adjoint of the matrix A. And if you don't remember what the matrix A was, that is matrix A, 8411. So we found the determinant and the adjoint, which is classified as our inverse. So let's do that. So as you can see, that is A inverse. And remember that we had matrix A, which is 8, 4, 1, 1. And we have matrix X, which is A, C, which are the unknowns. And it's equal to A inverse, which again you're seeing on the screen, multiplied by B. And again, when you multiply the inverse of a matrix by its matrix, it will give you an identity matrix. So all of this will give you the identity matrix. So in other words, this left side of the equation over here, and this aspect of it will give you the identity matrix, which you're seeing down here. Sorry for the bad scribbling. I can't help it every now and then. But that's how you get the identity matrix. All right? So it continues. Okay. All right. So that gives us the matrix I times the matrix X, and it's equal to the inverse of A multiplied by the matrix of B. Now, what does all of this give us? You might say again, all of this is long, but it's just a proof, and then you can simply just go to a particular stage and get your value or your unknowns quicker. But this is just the reason behind everything to show you how we actually multiply or use the inverse matrix to get our answers. So when we do this, so the unknown, which is our matrix X, which is on the left side, is equal to the inverse of A multiplied by the matrix of B. So what does that give us? 8 times 1 is 8, minus 4 times 1 is 4. So we have that, the determinant, and we have the adjoint. So again, it is crucial for you to understand how to find the inverse using the determinant and the adjoint of a matrix. And also using the resultant matrix, which is 280 and 50. So we continue. We get a quarter. The 4 is our determinant of A. The 1, -4, -1, 8. That's the adjoint of A. And matrix B is 280 and 50. So we need to row by column. So 1 times 280, and it's added to -4 times 50. Now, what will I multiply the -1 by now? What value or what element will I multiply -1 by? What do I multiply -1 by? There? There? Here, repeat. -1 times.
The 4, the -4.
Remember, row by column. Row by column.
280.
280.
Yes, 280. So row by column, that's so crucial in understanding matrices. So it's -1 times 280 added to, what would I multiply the 8 by?
8 times 50.
The what? Can't hear you. What did I multiply the 8 by?
50.
50.
Okay, 50.
50.
All right, and then you do the computation. 1 times 280 is 280, and then we have minus 200, -280 plus 400. So we have further computations to do. 200 from 280 is 80, and -280 added to 400 gives you that answer. Well, when you get it. So what do we do with a quarter? Remember that this quarter is literally what we call our scalar value. So we multiply a quarter by the 80. In other words, 80 divided by 4. And the quarter multiplied by 120. In other words, 120 divided by 4. Now what does that give us? It gives us that A is equal to 20 and C is equal to 30. Now what does A represent again? Can anyone tell me what the A represents? What did
Adults.
Adults. And what does the C represent?
Children.
Children. So when we get the 20 and the 30, how much tickets we got? 20 and 30. 20 added to 30. How much tickets we
60.
get?
60.
60. 20 and 30. 20 plus
Wait,
30.
sorry, 50.
50.
50.
All right.
Sorry.
So remember, where did we get that 50 from? It was the total number of tickets, right? And when we multiply 8, when we have 8 times A, which is 20, plus the 4 times 30, how much does that give us? 8 times 20 is how much? 8 times 20. 8 multiplied by 20 gives you?
820.
160.
160. And a 8, and you know, just put a 8 and a 2 and a 0. Yeah? 4 times 30 gives you 120. What does both of these values give you? 160 added to 120 is what? 280.
280.
So where did we get that 280 from? It was given in the first part of the question, was it not? So, again,
Yeah.
check your answers. Don't just leave it up for granted and say, oh, I still work it, man. I miss I work it. Yeah, man, anything them say goes. No, you need to check it for yourselves as well. You will learn better and you will retain more when you're actually putting the thing back, proving your things, and make sure they are correct. All right? Now, so that was the value of A and C, by the way. So that is how we actually use the inverse matrix method. All right? So I will leave you with a question, not this question. Give it a second. Let me just find which question I want to give you all. Okay. I want to give you this one. Okay, this one. I want to leave you all with this question. You can take the screenshot. All right. Do we all have it? Do we all have it?
Yes, sir. Yes, sir.
All right.
Yes, sir.
Okay, nice. All right. So that is that question, right? So the other thing I want to leave with you is a summary. Just let me get to it. Just to make sure you take away a few things from this particular session. So to calculate the determinant of a matrix, and the evaluation is also in the chat. So to calculate the determinant of a matrix, you want to find the difference between the products of the leading and the non-leading diagonal. In other words, whenever you see det, whatever matrix, it means determinant. So you have AD minus BC. So AD is the leading diagonal, BC is the non-leading diagonal, and you will subtract those two values. To find the adjoint of a matrix, you will interchange the leading diagonal elements and multiply the non-leading elements by -1. So whenever you see ADJ of a matrix, it means that you're finding the adjoint of that matrix. And this is how we generally calculate matrix. Using the inverse matrix method, we use the inverse of the matrix. So the inverse of the matrix is given by the reciprocal of the determinant of that matrix multiplied by its adjoint. And again, we use this to solve simultaneous equations. So another thing to note, matrix equation is AX, matrix A times X, matrix X, sorry, is equal to matrix B. So they can ask you a question to say, oh, write this in the form of matrix, of the matrix equation, and this is what they make reference of. All right, and also to make it a little simpler, the inverse matrix method is really saying that the unknown matrix is equal to the inverse of the matrix multiplied by the resultant matrix, which is B. All right, so you can use other letters, but we generally use matrix B. So, and also finally, when you multiply matrix A by an identity, it gives you identity multiplied by the identity matrix multiplied by the matrix A, and A inverse, the matrix A inverse of A multiplied by its matrix gives you the identity matrix. And again, these are just some proofs as it pertains to how we got the matrix X equal to the inverse of A multiplied by B. So I leave it all with that. You can always go to YouTube channel. Just type in Region 1 Math Team. You can even type in Matrices Part 1, Part 2, whatever it is. If you have a younger sibling, younger relative, cousin, etc., you can always check our YouTube channel. We have some PEP 6, PEP 5, PEP 4 content that they can interact with as it pertains to mathematics, of course. So that's all for today. And I will see you all in the next one whenever we have that. I would believe in December. All right? So all being well, that is it from me. All right? And have a good rest of the night, everyone.
Same to you.
All right. Thanks much.